Viewers, you're welcome to Science Spectrum with Don. This is PHY 187, the fundamentals of physics. So this will be the fourth part of the second lectures in derived physical quantities. Alright, we stopped in density, so I will proceed from here. So of course there are other physical quantities like momentum. Momentum is simply is the idea of a mass in motion, and of course is given by the product of the mass of the object times its velocity. Mass is in kilogram, velocity is in meter per second. So momentum has this unit, kilogram meter per second, and of course its dimension would be m for mass, l for length, then t raised to power minus 1 enclosed in a square bracket. Of course, we could have impulse. Impulse is simply the product of the force times the time in which the force acts. So force is meant to be in Newton and the time is meant to be in second. But of course, force itself is the product of mass times acceleration. So we could say Newton is the same as kilogram. Newton is the same as kilogram for mass, the meter per second squared for acceleration, then we multiply by second times second raised to power 1. And of course this would boil down to be kilogram meter per second, which is, it looks pretty much like the same unit as that of momentum. So impulse is kilogram meter per second, or we could say it is, in terms of its derived units, you could say it is the same as Newton times second, which of course is the same as that of momentum. So it will have the same dimension as m, l, t raised to power minus 1. And of course we could go to other derived physical quantities, like surface tension. About this. Surface tension is simply force per meter. So we have surface tension. Surface tension is defined as force per unit length. So force is Newton, that's product of mass times acceleration, and of course length is in meter. So this will give us this in meter. So this is kilogram for mass, meter per second squared over, this is meter. So I lose the meter, so we are left with kilogram per second squared. So surface tension, when expressed in terms of its equivalent SI units, would be kilogram per second squared. Or, if given in terms of its derived unit, we could say it is the same as force per meter. And of course, these are equivalent in regards to the SI and the derived unit. Of course, the dimension will be m for kilogram, t for time, and of course, this is raised to power minus 2. All right, now I could switch to electric field. Electric field, at times they use the word electric field intensity. Electric field intensity. This is just a representation of what happens around a charge that makes, let's say, take for instance a test charge to feel the influence of another charge pretty close to it. Alright, electric field is defined as force, the force expressed by a test charge divided by the test charge itself. Force is in Newton, and charge is in Coulomb. But Newton is the same as mass times acceleration, so that is kilogram meter per second squared. And of course charge is the product of current times time. So we get current is in ampere, and of course time is in second. So that's ampere second. And of course if I were to write this, we would get kilogram meter per second squared. Now everything I have downstairs becomes raised to power raised to a negative power, and I have this. So we could get kilogram meter per second raised to power 3, second raised to power minus 3, law of indices. Pick one of the bases that are the same and you add up the power, then I have per ampere. So electric field or electric field intensity, when expressed in its SI units, would be the same as kilogram meter second raised to power minus 3 per ampere. And of course, if given in terms of its derived unit, we could say it is the same as Newton per coulomb. And of course, its dimension would be m for mass, L for length, T for time raised to power minus 3. Then of course for current, that is I, that's I raised to power minus 1. And of course, we also have a electric flux. This is the amount of electric field, or a measure of electric field that penetrates a given surface. A surface with a cross-sectional area. So electric flux is electric field times the area it penetrates. That is electric flux. And of course, electric field is kilogram meter second raised to power minus 3 per ampere. Then times the area it penetrates. Area is given in square meter. So this becomes kilogram meter times square meter, meter raised to power 3, second raised to power minus 3. Then of course we have per ampere. Or we could say, since electric field is Newton per coulomb, of course area is in square meter, so this will be Newton square meter per coulomb. So this is, or we say it is Newton square meter per coulomb. So this is the derived unit for electric flux, and this is its SI base unit equivalent. Of course, the dimension will be m for mass, L raised to power 3, T raised to power minus 3, then ampere is current, that is either the dimension raised to power minus 1. Alright, having said this, we will talk about other physical quantities that are derived. Take for instance, magnetic field. At times they use the word magnetic induction, or they might use the word magnetic field density, as you like it, or magnetic field, okay? Or, okay, this is magnetic field, or at times you could see magnetic flux density, so to speak, magnetic flux density. They are the same. So what is magnetic field? I could draw this off now. Magnetic field is just a representation of what happens around a moving charge, or, so to speak, a magnet, as you like it. Alright, magnetic field. So I would still go with this, derived, the units, and for the dimension. Magnetic field is defined. The magnetic force on a moving charge is the product of the charge times its velocity or speed times the magnetic field. Of course, there is a factor of sine theta here. So if you divide both sides by the charge and the velocity, of course, you could see that magnetic field becomes force over the charge times the velocity. Force is in Newton, charge is in coulomb, and velocity is in meter per second. So the second comes up here, and the meter stays down. So if I could express this now in terms of its base unit equivalent, Newton second per coulomb per meter. Newton is kilogram meter per second squared. Then I have times second raised to power minus 1 here, times second raised to power 1 over coulomb is the product of its the unit for charge. That's current times time. So current is in ampere, time is in second, and I have, of course, the meter here. And of course, I lose the meter, I lose the second. So I'm left with kilogram second raised to power minus 2 per ampere. So Magnetic field or magnetic flux density, when expressed in its SI unit equivalent, it is kilogram second raised to power minus 2 per ampere, or like we've seen here, it is Newton second per coulomb per meter. And of course, nobody uses any of this to represent the unit for magnetic field or flux density. Rather, we use the unit Tesla. So 1 Tesla would give you one of these unit equivalents. Alright, now we could proceed to magnetic flux. Magnetic flux is the amount of magnetic field that penetrates a local area. So magnetic flux is simply magnetic field times the area it penetrates. Magnetic field, we've seen right in our own eyes in terms of its SI equivalent, it is kilogram second raised to power minus 2 per ampere, and of course area is in square meter. So if we define magnetic flux in terms of its SI base equivalence, we get kilogram square meter second raised to power minus 2, then we have per ampere, or we could simply say it is Tesla meter squared. So this is the same as, say, it is the same as Tesla times square meter. That is, and of course, Tesla square meter has a precise word for, or unit with which we represent this. That is called the Weber, and this is the official unit with which we represent magnetic flux. So, if we represent it in terms of the dimension, we have m for mass, L raised to power 2, T raised to power minus 2, and of course this is ampere, that's current, raised to power minus 1. And once I enclose this in a square bracket, it tells us that that is its dimension. And of course we could go to electric potential. There are others, electric potential, electrostatic potential energy. We could also have inductance. We could have resistance, resistivity, conductance, and of course the list will go on and on just like that. So we go to electrostatic potential energy. Electrostatic potential energy. This is the work you do in bringing a positive test charge from infinity to a point where it feels the repulsive force of a similar positive charge. And of course, it's the same work that the electric force will do to repel it away from where it feels the influence of the force. So this is work, and of course work is in joule. So what is simply work? Work is the product of force times the distance of displacement. This is in Newton, and of course this is in meter. Of course we call this a joule. But I like to express it in terms of its SI unit. So this becomes kilogram meter per second squared. Then times the meter here, make this a square meter. So we have kilogram square meter per second squared. Kilogram square meter per second squared. Of course, we call this joule. That's the units for work. Then we have electric potential. Electric potential is simply the work done per unit charge. So it will be this term divided by charge, and charge is current ampere times time. So this would boil down to be kilogram meter squared per second squared. We have per ampere per second. This gives us kilogram squared meter second raised to power minus 3. Then we have per ampere. And of course, this is defined as joule per coulomb, work done per unit charge. And of course, the official unit would be volts, named after the great Alexander Maestro. That's the great Alexander Volta. Of course, I will wrap it up here just for the sake of YouTube's policy of not uploading a video that is above 50 minutes. But in our subsequent bulletin, we'll go ahead and explore more of this, the derived quantities, their units and their dimension. Please, you may want to like, share, and subscribe to this channel if you're new. Thank you.